In this video, we are going to talk about inverse functions. Properties of inverse functions. So for any one-to-one functions, f of x equals y, a function f inverse of x, which we denote with a little -1 in the superscript between f and its argument of x, is an inverse function of f of x if f inverse of y is equal to x. This can also be expressed as f inverse composed with f of x is equal to x for all x in the domain of f. So in other words, if we compose a function together with its inverse, what we get back is the identity function. And that's like the idea of an inverse function. It undoes whatever the original function did. So that way, when we compose the two functions together, all we have is the identity function, where, whatever we input, we just get back what we input. That's what it means to be the identity function. It just spits out what you put in as the output. And so it also follows that f of f inverse of x is equal to x for all x in the domain of f inverse. And it is important to note, a bit of notation here. So f inverse of x is not going to equal the reciprocal of f of x, which is 1 over f of x. And you can also see the reciprocal written as the whole function in parentheses or brackets, and then raised to the power of -1. That's just what it means to be the reciprocal, which is drastically different from the inverse. And the other thing to note is that the range of f is going to be equal to the domain of f inverse. And the domain of f is going to be equal to the range of f inverse. All right, and so now we have some examples. And so in these examples, we are going to be given a function f and a function g, and we are going to try to determine if g is equal to f inverse. And so all we are going to do is check the composition f inverse of f of x, or rather in our cases here, g of f of x, and see if we end up with the identity function when we compose those two functions in that way. And if we do, then g is equal to f inverse. And if we don't, then g wouldn't be equal to f inverse. All right. So in our first of these examples, it wants us to let f of x equal 1 over x plus 2 and g of x equal 1 over x and then minus 2. And it wants us to check and see if g is equal to f inverse. So again, we are just going to check the composition here. So, and again, according to what we said above, and since f is going to be a one-to-one function, we can check the composition in either order, and we should end up with the identity function if g is indeed the inverse. But according to what we said, we are just going to check the composition going this way. So with g being the outer function and f being the inner function, and we are going to see if we end up with the identity function. And if we do, then g is the inverse of f. So we are going to check g of f of x. And so this is going to be equal to g of, and then considering the formula or rule of assignment for f, so g of 1 over x plus 2. All right, and so we are just going to now look at the formula for g, and we are going to replace every instance of x with 1 over x plus 2. So this is equal to 1 over, and then replacing x with 1 over x plus 2, it's going to be over 1 over x plus 2. Okay, and then we still have our minus 2 over here. So here we have a fraction of a fraction. And that might seem a little daunting, but the way we can view this is division is like multiplication by the reciprocal. And so here we're dividing 1 by 1 over x plus 2. And the reciprocal of 1 over x plus 2 is just going to be x plus 2. So dividing by 1 over x plus 2 is the same as multiplying by x plus 2. So what we really have here is x plus 2 times 1, which is just going to be x plus 2. So this equals x plus 2, and we still have our minus 2 over here. And we can add the like terms now. So we have 2 minus 2 is going to be 0, so we just have x. And so this confirms that g is the inverse of f. So I'm just going to do a little implication arrow to say that g is equal to f inverse, according to our verification process here, right? In the next example, so it says, if a is a real number, show f of x, which is equal to x plus a over x minus 1, where x is different from 1. This just has to deal with the domain of f here, so it's not going to include 1 in its domain because we can't have division by 0. So we want to show that f of x is its own inverse. That is, show f equals f inverse. So just like before, we are going to check the composition, except this time, we are composing the same function with itself, because here we are thinking that it is its own inverse. So we are going to check f of x and see if we again end up with the identity function. And here, if we do, then, well, that means that f is its own inverse. So f of x is going to be equal to, well, f of, and then here, I already know that we are going to be worried about spacing in doing this problem. So let me move that up. This is going to be equal to f of x plus a over x minus 1. Just replacing f of x with its formula or rule of assignment. Okay, and then now we want to go through and replace every instance of x in the formula for f of x with x plus a over x minus 1. So doing that, we are going to have, well, x plus a over x minus 1, and then plus a in the numerator. So that's just replacing this instance of x in the numerator with x plus a over x minus 1. And then doing the same thing in the denominator, we are going to have x plus a over x minus 1, and then minus 1. Okay. And so now to start trying to simplify things in both the numerator and the denominator, well, we want to add the terms that we have in the numerator and the denominator. And so to do that, we are going to have to create a common denominator. So here in the numerator, we have x plus a over x minus 1 and then plus a. So in order to add a to this fraction here, we are going to have to give a common denominator. And the way we do that is, well, we can think about a as being the same as a over 1. And then we can multiply both the top and bottom by x minus 1. And similarly, in the denominator, so to subtract 1 from x plus a over x minus 1, we are again going to need a common denominator. So what we can do is we can pretend minus 1 is the same as minus 1 over 1 and multiply both the top and the bottom of that by x minus 1. And so doing that, we are going to end up with, well, x plus a over x minus 1, and then plus, so we will have a times x minus 1, so distributing a over x minus 1, we have a times x minus a. And then in the denominator here, we are going to have over x minus 1, okay? And so in our main denominator now, though, we are going to have still, well, our first term will be x plus a over x minus 1. Nothing changed there. And then we have minus 1 over 1 times x minus 1 over x minus 1, which is going to be, well, minus x minus 1 over x minus 1. Okay. And now we can start trying to add things up in both the numerator and the denominator now that we have a common denominator in both places. So in the numerator, well, we just add the terms across the two numerators and these fractions up here in the numerator. And so we are going to have x plus a times x minus a. So a and minus a are going to cancel out, and we're just going to have x plus ax. And this is still over x minus 1. And then in the denominator, adding things up here, so we are going to have x plus a, and then minus x, and then minus a negative 1. So that's going to be like plus 1. So we have x minus x. Those guys are going to cancel out. And then we have a minus a negative 1. So a plus 1 is the numerator of the fraction in the denominator. And its denominator is still x minus 1 as well. So that's what we have after we combine the terms in the numerator and the denominator. And so let's see if we can start trying to simplify things even more. So again, whenever we have division by something, we can think about that as being the same as multiplying by its reciprocal. So here we are dividing by a plus 1 over x minus 1. So we can think about that as being the same as multiplying by its reciprocal, which is going to be x minus 1 over a plus 1. So this is going to be equal to, well, the numerator is still just going to be x plus a times x over x minus 1. And then multiplying by the reciprocal of the denominator now, we are going to have x minus 1 over a plus 1. And so this allows us to see that we can cancel out the x minus 1s with each other. So those guys cancel out with each other under multiplication. And so what we are left with is going to be x plus a times x over a plus 1. And then from here, we can factor out an x from each of the two terms in the numerator. And we aren't talking about fractions of fractions anymore. So, it's not like we have a whole, it's not like we're talking about numerator over numerator here. So, yeah, we're just talking about the numerator. So factoring out an x from each of those terms, we are going to have x on the outside. And then what's left is going to be 1 plus a. That's after we peel off a factor of x from both x and a times x. And then over a plus 1. We could rearrange the terms here. So we could rewrite 1 plus a as a plus 1. But we are running low on space. So I'm just going to say, addition is commutative, meaning that we can add things in any order and we will have the same thing. So that means that 1 plus a and a plus 1 are going to be the exact same thing. In other words, these guys are going to cancel out. And so what we are left with is just x. And so this finally shows that f is equal to its own inverse. So f equals f inverse, which is kind of neat. Right. So that's how we verify if two functions are inverses of each other. We can just check the composition of the two functions and see if we end up with the identity function. Now let's talk about finding inverse functions. So if we want to find the inverse of a function represented by a graph, all we would do is interchange the x and y value of each coordinate from the graph of the original function to find the corresponding points of the inverse function. And so this is equivalent to just reflecting the graph of the original function across the line x equals y, or y equals x. But if we are trying to find the inverse of a function represented by a formula, well, that's going to be sort of like a three-step process, if you will. So first, we want to make sure the function is one-to-one. So we can check that with a graphing utility if we want to, and just verifying that its graph will pass the horizontal line test, confirming it's one-to-one. And then once we do that, we will interchange x and y. So the first thing, like if we are using the functional notation, we are going to replace the function's name, which is y. And once we do that, we will interchange x and y. And then once we've interchanged x and y, we will have a new equation, which we will solve for y. And once we've solved for y, we will have the formula for the inverse function. Right? So we have two examples here. So in this first example, we are asked to find the inverse of the function f of x equals 2 over x minus 3 plus 4, where x is different from 3. Again, this is just having to do with the domain of f here. We can have division by 0, so 3 has to get excluded from the domain of f. So the first thing we are going to do, so we aren't going to check if the function's one-to-one. I'm just going to say straight away that the function is going to be one-to-one. If you want, you can check the graph of f here in a graphing utility, and you'll see that it will pass the horizontal line test. So with that out of the way, let's go ahead and copy down the formula for f of x, but instead of writing f, we are going to write y on the left-hand side. So we have y equals 2 over x minus 3, and then plus 4. Okay, and then now just like the steps say, we are just going to interchange x and y in this equation here. So doing the interchange, I'm going to just arrow over here. We are going to have the equation x equals 2 over y minus 3 plus 4. Okay. And now we want to start solving for y. And so the way that we can get this expression involving y out of the denominator here on the right-hand side is by multiplying both sides of the equation here by y minus 3. So if we multiply both sides of the equation by y minus 3, well, on the left-hand side, we're going to have x times y minus 3. And on the right-hand side, we'll have 2 over y minus 3 times y minus 3. So the y minus 3's will cancel out, and we'll just have 2. That's what we were trying to accomplish here, just getting that y minus 3 out of the denominator so that we would have a chance to eventually solve for y here. And then plus, and then we have 4 times y minus 3 still, so that's just going to be 4 times y minus 3. We'll worry about distributing in the next step. Okay. So now let's go ahead and distribute. So we have x times y minus 3x on the left-hand side equals 2, and then plus 4y, and then 4 times minus 3 is going to be minus 12 on the right-hand side. So we can add like terms real quick on the right-hand side. So we have x times y minus 3x equals, so 2 minus 12 is going to be minus 10. So we have 4y minus 10 on the right-hand side. And now let's try to get all the terms involving y on one side of the equation and all the terms not involving y on the other side of the equation. And so to do that, we can subtract 4y from both sides and add 3x to both sides. So minus 4y plus 3x minus 4y plus 3x. Adding these guys up. So on the left-hand side, minus 3x and 3x is going to cancel out. So we're just going to have x times y and then minus that 4y. And then on the right-hand side, we have 4y minus 4y. Those guys are going to cancel out. And so we will just have minus 10 plus 3x, or in other words, 3x minus 10. All right. And then now, so what we can do from here, so on the left-hand side, each of these two terms involves a factor of y. So let's go ahead and peel off that factor of y. And once we peel off that factor of y from each of those terms on the left-hand side, what we're left with is, well, x minus 4 in the parentheses. And then equals 3x minus 10. And so finally, the last thing that we can do to get y by itself on just one side of the equation is just divide both sides of the equation by x minus 4. And so that's going to give us y equals 3x minus 10 over, I think it was a little too greedy to try to fit that underneath there of me. So let me just arrow over here. So we will have y equals 3x minus 10 over x minus 4. And if we wanted to, we could go back and we could check, just like we did in the two examples on the previous page. We could check the composite of what we found with our original function and see if when we compose those two guys together, if we end up with the identity function. And that in that way, we could verify, that everything we did here was correct and that we do have the inverse. For the sake of time here, though, we aren't going to go through the verification process here. Just going to go ahead and say that this is f inverse of x. So f inverse of x is equal to 3x minus 10 over x minus 4. Though if you want to, I of course encourage you to, on your own, go and verify that this is indeed the inverse of f by checking the composition. And what you'll find is that we end up with the identity function. All right. We have one more of these examples, and we'll wrap up with the section. So in the next of these examples, we are asked to find the inverse of the function f of x equals h plus the square root of x minus k over a. And this is for x greater than or equal to k. Again, this just has to do with the domain of f here. Since we have the square root going on here, we need the expression under the square root to be non-negative in order for us to have a real number value for f. And so that's going to happen when x is greater than or equal to k. So that's just about the domain. So again, trying to find the inverse. So let's go ahead and write y equals h plus the square root of x minus k over a. And I will point out, so our function f here is a one-to-one function. That is, it does pass the horizontal line test. The function we are going to find for its inverse, though, is not going to be a one-to-one function. It's going to end up being a quadratic function, which isn't going to pass the horizontal line test. So its inverse is going to be just like a one-sided inverse in the sense that the original function f has an inverse, but what we find as its inverse doesn't have like an inverse in the true sense because it is not a one-to-one function. All right, so now we want to swap x with y. So doing that, we are going to have x equals h plus the square root of y minus k now over a. Yeah, and actually, if any of you are familiar with the vertex form of a quadratic function, you're going to see this h, k, and a floating around here in the formula for f of x, and you're going to be kind of suspicious that maybe the quadratic function we're going to end up with is like, just the standard quadratic function in vertex form. And if you have that suspicion, well, it's right. So let's see that. So let's start trying to solve for y. And so here to start trying to solve for y, well, what we can do is we can square what we have under the square root. Let me go ahead and say that this is for y greater than or equal to k. We can square what we have under the square root here. And doing that, well, on the left-hand side, we are going to have x squared and then equals, well, actually, wait. Yeah. Here, let's hold up and wait to square it because we will save ourselves some work if we just subtract h from both sides first. So subtract h from both sides and then we'll square both sides. So subtracting h from both sides, we're going to have x minus h and then equals the square root y minus k over a. And now we're going to square both sides. And by the way, so if you ever take the square root of a square, what you end up with is the absolute value because you don't know if that square was a negative or a positive to begin with. But when we are squaring the square root, we don't have the absolute value because, again, we are already assuming that what we have under the square root here is positive. So squaring the left-hand side, we're just going to have x minus h squared, or we'll worry about foiling this out in the next step. And then on the right-hand side, well, we are going to have just y minus k over a. And the way we can see that as well, so maybe here in the previous step, instead of using the square root, we could have said that this is equal to y minus k over a to the 1/2 because that's all square rooting is. And so that's why we're squaring both sides because taking the power of a power gives us the product of the powers. And of course, 1/2 times 2 is going to be 1. So the exponent just simplifies down to 1 when we square both sides, on the right-hand side, that is. And again, that's from the exponent property that says that power of a power is equal to the product of the powers. All right. And actually, we don't have to worry about foiling out x minus h squared. I think we rather just keep it like that because, yeah, we are working towards representing or writing the quadratic function in the vertex form, just the general quadratic function in the vertex form. So let's try to solve for y. So to do that, well, the first thing we want to do is multiply both sides by a. So multiplying both sides by a, we are going to have, well, a times x minus h squared on the left-hand side, and then on the right-hand side, the a's will cancel, so we just have y minus k. And then let's go ahead and add k to both sides. And we'll finally have y by itself on one side. All right, so on the right-hand side, we just have y now, and on the left-hand side, we have a times x minus h squared plus k, which again, those of you familiar with a quadratic function in the vertex form will recognize what we have on the left-hand side as just a general quadratic function in vertex form. So its vertex is h comma k. All right, and so let's go ahead and we can now say that f inverse of x is going to be equal to a times x minus h squared plus k. Okay, and that's it for that's it for inverse functions.